All right. In the last video, we talked about length or distance between vector, or we talk about length, which is the same as distance. The whole thing. And we looked at I showed you two vectors, and then I subtracted them, and I showed you the distance there. And the reason this works, so if we want to know the distance between two vectors, so that is, if I have some vector here, and I have some vector here, and I want to know this length here, which would be the distance between those two vectors. Well, what I actually have to do is take one of the vectors and subtract the other one. Now, another way to define that subtraction, right? If this is u and this is v here, one way, so u minus v is also defined by u plus the negative of v, right? So the negative of v here would be this way here. And if I add those two things together, you see I get this here, and that didn't help at all. That should be that. It's not that. Oh, no, that's because I totally screwed the pooch on that one. Right, when we add our vectors together, we put them end to end. Oh, goodness. So if I put this vector here, then this would be our product. Here we go. There's our adding. Okay, we'll get rid of this guy. That guy's not what we want. This would be the added product here. Hey, that's u minus v there. And just go with it, which is the same as this one here. Hey, okay. So in other words, the distance between two vectors is just the length of the difference of those vectors. And because we're talking about distance, it doesn't matter if you do v minus u or u minus v. You're going to square these things, so it doesn't matter what the sign comes out to be. All right, so we're going to find the distance between 7, 1 and 3, 2. So first thing we need to do is find u minus v. So u minus v, I'm going to take my 7 minus 3 is 4. 1 minus 2, negative 1. And again, it doesn't matter. I can do this in any order. I'll show you. So the magnitude of u minus v is 4 squared plus negative 1 squared, 16, 17. Square root of 17. Right? It doesn't matter. I can do v minus u. Right? V minus u would be 3 minus 7 is negative 4. 2 minus 1 is positive 1. And then again, it doesn't matter. V minus u. Oh, goodness. Writing is hard. Is this time, though, it's just negative 4 squared, but that doesn't change the fact that it becomes a positive number, and it becomes a 16 anyway. So this is still square root of 17. So it doesn't matter the order you do those in, you're going to end up there in the same fashion. All right, the reason we started talking about this idea of dot products is that they actually cause us to, they tell us a little bit about the relationship between our vectors. In particular, one of the relationships that they can tell us is whether or not our vectors create a 90-degree angle with each other. In our traditional geometry system, right, we talk about when they're 90 degrees, we call that perpendicular. We have a new name for this now. It's called orthogonal. So you may have heard the word orthogonal. It means perpendicular, but orthogonal just means perpendicular in the sense that we can have more than two dimensions. So all these things are 90 degrees to each other, and it doesn't matter that they're not on a plane and whatever. So orthogonal extends it to additional dimensions. Perpendicular is only if you're in R2. And it turns out that if my vectors are orthogonal to each other, their dot product is going to be 0. So let's think about this, right? So two vectors that we know are orthogonal are the unit vectors that make up our xy axis, right? So this vector here and this vector here, right? We know that the x and y axis is always going to be perpendicular to each other. And so this is the vector 1, 0, and the green one is the vector 0, 1. watch what happens if I take their dot product. Right? Their dot product is just what happens when I take the first entries, so 1 times 0 plus 0 times 1, and I get 0. Okay, I could also do this if we go in the opposite direction. So maybe let's take the vector instead. We'll go 1, 0, and 0, -1. Okay, we'll take going along the y-axis in the opposite direction. And again, we're going to have 1 times 0, 0 times -1. This dot product is going to give us 0. Right? So anywhere in the plane. So, and even if I scaled those, if I extended those, we could certainly take other vectors here. So another option, we know that the line y equals x and the line y equals -x are perpendicular to each other, right? So if I go this line here and this line here should be perpendicular to each other. And if I pick some vector that's on either of those, so let's say, I don't know, the vector 3, 3, and the vector, I don't know, -2, 2, right? That would be somewhere over here. Hopefully you can see that, again, I'm going to be multiplying the same product, but because this one's negative, I'd have -6 plus 6 is going to give me 0. So no matter what, if our vectors create a 90-degree angle to each other, their dot product is always going to be 0. And oh, hey, look, I did this example without even realizing I had left this example up. So, hey, look, aha, 2 vectors that are orthogonal to each other. Another way to handle this is just picking values that you know. So, I don't know, if I set it equal to 0, let's say, I don't know, 2 times 3 gives me 6, right? And I don't know, -1 and 6 give me 6. Give me -6, that would give me 0. So if I take these two as components, 2, -1, and 3, 6, those would be perpendicular to each other, because their dot product would be 0, right? 6 and -6 add to 0. I could also, or the same idea, we could take 2 and the 6th, and then 3, -1. Those would also be perpendicular to each other, because their dot product is still 0. So lots of options there. The Pythagorean theorem, okay, so this is 100% directly related to exactly what we talked about in finding the distance to begin with. 2 vectors are orthogonal if and only if the magnitude of their sum, or the distance along their sum squared is equal to each of their bases squared. Okay, you ready? So if they're orthogonal, here's a fun fact, right? So here's U, here's V. We're assuming they're orthogonal, which means that this here is U plus V. Okay, it's always going to be, if I take the diagonal there is always going to be right? What happens if I create and finish that parallelogram? So that would be U plus V there. And I don't know, can you see that this is a Pythagorean theorem triangle? So V squared, or the magnitude of V squared, right? V would be the length here, plus the magnitude of U squared. That would be the sides of the bases of our right triangle should equal the hypotenuse squared. And on our hypotenuse is U plus V. So square those vectors, length, and ta-da! Yay! Pythagorean theorem, realized, actualized. Love it. Gotta love it. Okay. All right, here's where we get into some different and interesting things going on here. And that's the idea of I'm spinning around, of orthogonal complements. So if Z is orthogonal to every vector in a subspace W, then Z is orthogonal to W. The set of those vectors is called the orthogonal complement, and we call it W, perpendicular of W, right? So right here we have in W, so in this picture, you see this line L right, is perpendicular to this this set right here, or this particular line right here. Now, what we're talking about is U is W, at least in this picture. W is represented by a plane, and Z is represented by a line. And Z could be, and my vector could be anywhere along that line, and anywhere along that line is still going to be perpendicular to that plane. Now I could also move that Z vector anywhere else, right? As long as wherever I move my L or my Z, as long as it's still perpendicular to the plane, then it's still a part of this subset W perpendicular, or W perp. Sounds like something you'd say when you're trying to bring somebody in for a crime. I don't know. But anyway, the set of all possible perpendicular vectors to this plane W, or to this subset W, is called W perp. And there's some properties here. So the first is that if your vector is in W perp, if and only if X is orthogonal to every vector in the set that spans W. Right? Now this is, so notice, set that spans W. The nice thing about that is that I don't actually have to show that X is perpendicular to every single vector in W, or every single thing in W. I just need to show that X is perpendicular to the set, or the basis, or the bare minimum of things that spans W, right? So whatever W is defined by, or whatever spans that, as long as I can show X is perpendicular to those things, then I can say that X is in W perpendicular, or W perp. The next is that W perp is a subspace of Rn, which hopefully kind of makes sense. All right, this one, angles in R3, in R2 and R3. So this goes back to that idea of the dot product, telling us if the dot product is 0, then it determines that these things are perpendicular. This relationship it comes up, and you've probably seen this more often than you think you have. But especially in like physics, if we're talking about doing a vector analysis of this, we're going to break this up into component vectors, right? Where you have the downward component and the forward component motion. And the way that we do that is by taking the full magnitude of this force and breaking it up using the angle here, so the angle theta. So what this says is that the dot product between two vectors is equivalent to the magnitude, or the length, of each vector times the cosine of theta, where theta is the angle between U and V. Right? So one thing this could do, we could use this to solve for the angle between things, right? So if we know what the dot product is, or if we know what the vectors are, if we know what the vectors are, we can find its dot product, we can find their lengths, and then we can solve for that angle. Or if we know the angle and we know the lengths of those things, we can figure out what the dot product would be. So either way, fun facts. Fun facts! Haha! I think that's it. Is that it? That's all. It's on this page, right? Oh, okay, cool. All right, now we're going to get into weirder stuff. It's fun. It's exciting.